Okay, so hello and welcome. Here we are again. Yet another problem. Here we go. So what I want to do is this, we're going to just out the gate, see how fast we can solve it. So this is binary tree maximum path sum. Let's see how we do. A path in a binary tree, oh wow, it's got a lot of upvotes, is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them. A node can only appear in the sequence at most once. Note that the path does not need to pass through the root. Oh, interesting. Okay. A pair of adjacent nodes in the sequence has an edge connecting them. So you could have an ancestor in two. We could define the paths as only sort of moving down the tree, or we'll call them directional paths. We only have two directional paths from an ancestor. Those paths those nodes are considered connected through a path. Path sum of a path is the sum of the nodes values in the path. The sum of a path is the sum of the nodes values in the path. Okay, fair enough. Given the root of a binary tree, return the maximum path sum of any non-empty path. Okay, interesting. So the optimal path is 2, 1, 3 with a path sum of 2 plus 1 plus 3 equals 6, 9, negative 10, 20, 15, 7. How are we doing on time here? Minute and a half. So I think I've seen a question like this before. I think I know what this problem is referring to. Basically, you could rephrase this problem as like, well, even a solution of the problem could just be, for each node there is a maximum path to the to any particular leaf node, maximum value, and then on the left side, left subtree, or just the left child from going down the left side, there's a maximum down the right side. If you just add the two for every node, you get the maximum for that node, and then you just take the maximum of all the nodes. And I think you probably can compute the maximum left side and maximum right side paths for each node in time that's proportional to the number of nodes. So we'd probably end up with like O of n memory and O of n time algorithmically. I'm not sure if I could do this with constant extra memory. Probably not. But I think we can do this, solve this relatively efficiently. We do it in linear in the number of nodes, and I think the logic will be relatively simple. We'll come back to that in a moment. We'll try to do this recursively. I think probably it would very likely only be done recursively. I don't know if there's probably a way to do this iteratively, but I wouldn't know that like offhand how I might do that. Okay, root -10. Okay, so this one we said. So this one would probably be, so from -10 we have 9 is the maximum to the left, 20 to the right is probably 35 to the right. So that would be 35 plus 9. Oh, plus 10, so it's -1. Actually, that would be 36. Plus the root, too. I forgot about that. You have to get the left, the right, maximums plus the root. 20, you have 35, you have 15 on the left, 7 on the right. It's 22 total. 42 gives you 42 total. So optimal path is 42. And there's 30,000 nodes in the tree, and they're between the values -1,000 and 1,000. All right, let's first try to find out, well, just like a depth path. So we'll do like max depth path sum or something, or depth sum, max depth sum, or we'll call it max sum, max, I don't know, leaf sum, or max path downward. Well, just m sum, I don't know. I'm not even sure what to call it. So what we're going to do is try to get the maximum, not path to any other node, but just path down to any particular root. That we can do, I think we do that recursively. Let's say if we had inductively that we knew the optimal path on the left side and the optimal path on the right side. Like those nodes, we knew all the optimal paths already for the left and right childs of the left and right child. Then the optimal path to this node, it's either the left side or the right side, right? You have to pick one for that node. And basically, you would say it's the root value plus the optimal path on the left, or up to the maximum of the optimal path on the left and the optimal path on the right. Every node will have an optimal path. So that's the thing I'm trying to think through. How are we doing on time? So I think I know the solution to this. I don't think it'll be too quick though. We'll see how we do. So basically, we just want the optimal path from a particular node to a root node. That's what we're looking for. Because if we do that, then we can say for every node, we can revisit every node and say take the left node's optimal path and the right node's optimal path, and now connect those, right, with the root node. Can we do all that in tandem? I'm not so sure. I think we might have to do at least just one quick routine, or not one quick routine, but one routine where we get the optimal path for every node, and then we can get the optimal path for every, then we can get what they're looking for. We just traverse the tree again. One question is, do we want to use an unordered map and save all of those values for every node? I think that's fine. Can we find the optimal path on the left? I mean, we can do this all at once. I think. I think we can do this in tandem. I think it's okay. So I think we can actually do this in one shot, but we can do F, we have tree node root, R, msum of R root, msum. This is going to return an integer, base case, if not R, return 0. We're going to say, so there's F of the left subtree, there's the right subtree, right? And we're going to say ret is the maximum of the current value, or it's going to be, so I'll say int left, int right, L, R, L plus R plus, oh, did that wrong, left, right, left plus right plus R val, and we're going to say return here, we're going to say the maximum of left and right plus this value. I think it's something as simple as that. I don't know. Let's try to run it and see what happens. But I don't think it's. There might be more to it than that. Well, at least there's that. I always forget to write the setup. I set up this, what this is called, the lambda expressions finishing. The lambda expressions finishing always forget to use the lambda expressions finishing semicolon. Oh, looks like we might be correct. Can we just generate some test cases here? All right, well that's pretty simple. So yeah, so the left and right, it's going to get you the optimal path to the left and the right, and then we just check against our global variable that the root against the left and the right. We just add those two together and add the root value, and then yeah, we just do it that way. So pretty straightforward. We'll just call it path sum. Is probably better than m sum, but I was thinking like max sum. Let's actually just go for it. I think it's probably correct. If it works in this case, I mean, let's just try some other test cases before we. I don't know, something like this. I think it is that simple, but all right. I think we go for it. I don't know. There might be something I missed. Oh. I did miss something, huh? There's always at least one. Totally didn't even think about that. Gotta test those test cases, man. The one, single nodes and the sort of the degenerate test cases. Oh, I'm so upset now. That was pretty quick. If I got it right, that would have been 12 minutes. All right, we'll try again. I don't know. There's got to be something I missed. Man. All right, whatever. Yeah, that's my mistake. I'm bad at this, man. I thought I got it really quick. I thought it was super clever. Alrighty. 4. Wait, 1, -2, 3. Hold on, what? Alright, I guess I'm not so slick after all. Oh, I got 3 though. -2, 3. Oh, I did miss something. Yeah, okay, that's subtle. That's a subtlety. It could be one of these. You could do this. Does that compile? 6. I did that wrong. There's got to be some other test cases. I don't know. I wouldn't know them offhand though. I have to sit and think about it for a while. Maybe I should do that. I don't know. Oh man, I'm getting destroyed. That's 3 wrong answers in a row. Oof. Oof. Part of the problem with this is this question is like all the different test cases that you wouldn't think of. I don't know. I'd have to like go through it, like think about all the things it might be. What could possibly go wrong? So this thing, we should get 10, but I got 7. So what's 10? Oh, and just the value itself. Yeah. All right. Fine. Come on, man. I wouldn't have thought of all that. No way. There's no way I would have thought of all those different situations. Oh, come on. It never ends. Brother. Brother. Come on. What is this? What is this? There's so many. There's so many. What? What are they saying? We should get 16. I got 15. All right. 16 instead of 15? What? All right. There's 15 here. What did I say? 16. So you can go 15 plus 4 gives you 16. So you can get this path. But how did we not get the right answer here? Actually, this, oh, that's why. All right. That's kind of a hard question, man. So if the paths don't have to go all the way to the bottom, that's the issue. So my idea was just wrong. Oof. 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 Yeah, so if this is 0, then you don't have to go all the way down. I think that might be the issue. Yeah. I don't know, man. I don't know. There's bound to be some other test case I missed. Okay. Come on, man. That was brutal. That was brutal. Oh. That was so brutal. That was the most brutal thing ever. I see why that's a hard. That's too funny. Look at this code, though. Look how concise that is. How beautiful that is. Oh, man. That was rough. We're fast, but we use a lot of memory. Apparently you can do this without using so much memory. I wouldn't have thought that. How do you, how does that work? I don't know. There might be a way to do this with, oh wow. Dude, let me hit the submit button a few more times. How do you do this without using so much memory? That's my question. Yeah, how do you do this without using so much memory? I think there's got to be a way to do this recursively, or not recursively, iteratively. Without using so much memory. Huh. I don't know, man. That's pretty. I mean, you can do like an in-order traversal with using Moore's traversal, right? Using threading. I mean, we've coded that before. The problem with that, though, is that in-order traversal wouldn't necessarily give you what you need. Yeah, because the problem with that is, I mean, you can maybe do a bottom-up approach. Maybe that's the way, but from the leaves. But you'd have to start at the leaves somehow. That's kind of what this is. I mean, this is top-down, but I want to say something like a dynamic programming solution, something like that. But maybe you don't need any. Maybe you don't need that much memory. Maybe you could do this like. I don't know, man. You kind of gotta. There's some kind of dynamic programming thing you can do. I don't know. Don't know it offhand, but that was really bad on my part. I probably should have. Should have guessed. A few modifications later. That was a hard one. We're gonna go for one more. All right, we got it. Yeah, that really was just like testing, but going through all the different test cases. There's a lot of just tricky test cases with that. All right, moving on. See, that was fun. I got whipped. I mean, I got beat. Yeah, thank you for watching. We'll go to the next problem. Let's do another one. Take care. Take care.